Dr. Ozay is an associate professor of electrical engineering and computer science in the University of Michigan. Also, she is a core member in Michigan Robotics. Dr. Ozay specializes in hybrid dynamical systems, control optimization, and formal methods with application in cyber physical systems, system identification, verification, and validation, autonomy, and dynamic data analysis. And today she is going to share with us her expert experience and opinions on the topic of self-autonomy with imperfect information. And please give your full attention to Dr. Ozay. And let's welcome Dr. Ozay.
Thank you very much for the introduction and also for the invitation. It's great to see some old friends and colleagues and collaborators here. And hopefully we will see each other in person in not too distant future. And I know it's quite late back in KAUST, so I will try to keep this talk a little high level so that we are not like too sleepy at the end. So we are talking about verification, and I will start by pointing out that complex autonomy software is out there in the wild. So one of the things that when I started doing verification research, it was very hard to find real software running on real vehicles. So typically, if you go and check older verification papers or formal methods papers, you will see people coming up with their toy models and trying to verify their toy models or toy problems. But currently, if you go to GitHub, you will see software stacks for real self-driving companies. So this is one of them, Apollo, a Chinese company. Their software stack is mostly open source in GitHub. So you can go and check out, for example, GitHub repositories of teams that participated in DARPA Urban Challenge and DARPA Grand Challenge. And they're fairly complex software stacks with thousands, if not millions of lines of code. And there's also this company, KAUST. I don't know if you are familiar with it. So they claim they can convert your regular vehicle into a self-driving vehicle, having almost the same capability as a Tesla autopilot. And they are selling these small devices. You can also make those devices at home by buying off-the-shelf components that you put on your windshield. And you connect it to your canvas and you download their code from GitHub and you have your self-driving car. And this brings an interesting challenge for all the verification research. So now we have real software. Can we scale our approaches to work with real software? So that was one motivation for us to see if we can do something in this domain. And the questions that I want to ask is that can we prove autonomous systems correct and safe given the software complexity? Or can we design provably correct and provably safe autonomous systems? And I want to give a high-level overview of different approaches in formal methods. Probably most of you here is maybe familiar with those, but I just want to show you what the landscape is. So when you think about formal methods, one of the holy grails is this verification problem, where you have your autonomous system plant model, then you have this complex autonomy software. This is coming from the GitHub repository with thousands of lines of code, if not millions. Then you want to develop this verification algorithm that takes into a plant model, that takes into a model of the software and a specification, and tries to give out a correctness proof. Or it tries to give out a counterexample saying, look, this plant with this type of autonomy software will fail to satisfy your specification. So what are the advantages and disadvantages of this approach? If it works, it gives you very strong guarantees. But in general, if you have a hybrid system where your plant model has continuous variables together with discrete variables, this is a computationally very hard problem. It's indeed undecidable in most cases. So oftentimes many verification techniques, they would either solve the problem, give you a correctness proof, give you a counterexample, or they will say, oh, I don't know, because I couldn't come to a decision. And one of the pieces that makes this problem harder is most of the complexity comes from the code. If you are dealing with relatively rigid autonomous systems like vehicles or robots, if you are not doing soft robotics, we have quite a bit of good tools for getting reasonable models for the physics. And our physics models are not that complex if you are dealing with standard, I would say, vehicles. But the software itself, it can be very messy. And software is hard to model, and it's hard to scale when you have this messy software. So what are different approaches? If verification is hard, what else we can do? So one alternative that I worked on quite a bit is correct by construction control synthesis. So what you do in this case is that you say, okay, software is complicated and it's likely buggy. I will just get rid of the software and I will try to synthesize it using an algorithm itself. So in this case, you have the plant model. You don't have software at all. You have the specification and you're asking an existential question. Does there exist a software or control policy when I close the loop around my plant model that will satisfy my specification? Again, the synthesis approach either gives you a policy controller with correctness guarantees and maybe a validity domain that tells you where this controller is guaranteed to work, or it gives you a proof of impossibility. It can give you a proof that says there exists no decision-making software that will achieve your spec. In which case you can go back to your design and you either relax your specifications or you try to improve your platform by adding more actuation capabilities. So what are the advantages and disadvantages here? Again, you have very strong guarantees if it works. It avoids the complexity induced by software because we are ignoring the software, but we are reducing the input complexity of the algorithm. We are increasing the output complexity because we are now trying to synthesize this complex thing. And one other advantage I would say is that it has this explainability aspect. It tells you about fundamental limits and impossibility. If your synthesis tool tells you that this is not possible, then you know, no matter how smart you are in designing your software, the problem doesn't have a solution. What are the disadvantages? Although you are working with a smaller input to the problem, computational synthesis is much harder because verification is a special case of synthesis. The specifications you can handle in synthesis are a limited set of specifications, and correctness and completeness of specifications in doing synthesis ends up being very important. I have quite a few stories where we synthesize something. It's correct with respect to the specification, but it does something stupid because our specification did not specify everything we intended to do. And this is partly due to our inability to think and write down the complete enough specification. And it's partly due to the expressivity of the specification languages that synthesis tools can handle. And one final disadvantage, that's a big disadvantage from my perspective, is there's almost no synthesis approach that works with perception and learning components. So you cannot really synthesize this perception and learning components in a provably correct way. Okay, so another alternative here is falsification, in which case what you do is, instead of getting these models, you work with a black box. You have your plant model and a software model in a black box in closed loop that you can query. You have your specification, and you are essentially searching for the counterexample. But if you cannot find the counterexample, the approach is inconclusive. So the advantages here is that you can handle arbitrarily complex models, this closed loop models, including learning-based components, because you are really agnostic to what this model is. You are just querying the model. And there are quite good tools out there adopted by industry that does falsification in a smart way. Of course, there are some disadvantages to this. As I said, if you don't get a counterexample, you don't know what's going on. And even if you get a counterexample, there's no explanation for this counterexample. So it can give you very trivial counterexamples if you are not modeling all the assumptions carefully. For example, in the case of self-driving cars, it can tell you if you are going with 70 miles per hour on a highway, and if a person jumps in front of you, then you will hit the person, therefore you are not safe. So there's this problem of not being able to capture all the interesting counterexamples. And the other disadvantage is that since you are putting everything into this black box, you cannot really locate where this fault is coming from. Is it a hardware fault? Is it a plant limitation? Or is it a software bug in my control decision-making logic? Or is perception doing something weird and that's why this is happening? So you don't have a sense of this thing because everything is a black box. You are just finding a software. You are just finding a counterexample. So motivated by this, we thought whether we can combine synthesis with falsification for creating some new design aids for safe autonomous systems. And I will try to talk about this in the second part of the talk, but I usually don't time my talks well. That's why I will show you the result first. Then I will try to build up and get you to how we come up with that result. And this is a very new result, so it's not super polished, but I think it's an interesting perspective. Okay, so we want to combine synthesis and falsification to develop a new way of doing falsification, where there will be some explainability. We will be able to do things more efficiently, and we will be able to work with learning-based components, with vision in the loop, and those sorts of settings. So here I have two Carla simulations. So this is a driving simulator with pretty high fidelity models and very good visuals for doing perception-based control. We trained the end-to-end neural network controller for a vehicle. And this controller tries to follow the lanes. And if it sees an obstacle, it tries to avoid the obstacles. The controller doesn't have, in this case, any control on braking, but it can do steering and try to avoid obstacles. So this is how that controller works. So this is a bird's eye view of what's going on. So your car starts from here, controller gets these images, it sees that there is a red Coca-Cola truck in front, and it tries to pass through it. And we run this controller with random noise to the image and this and that, and the controller performs pretty well. So we tested the controller a little bit, and it performs pretty well. Now, in the bottom, you will see the same controller with our falsification technique modifying the images a little bit. And let's see what happens in this case. So using this idea of combining synthesis and falsification, we can find out how to modify this image so that we can fool a controller. And I will try to explain you how we do this. And our synthesis approach has no idea about the underlying controller, but it can query the controller and does that querying in a smart way. And I will try to tell you how it does. Okay, so before telling you how we do this, I will switch gears a little bit, and I will try to talk a little bit about how we get there. So I think the key step in designing safe autonomous systems and combining the synthesis and falsification is understanding structural properties of maximal safety controllers in different information regimes that are common in autonomous systems. So Marco talked a little bit about this. Both Marco and Sam, they talked about this barrier functions and Hamilton-Jacobi-based controllers. They are in a sense all controlled invariant sets. And I think the interesting and mostly open question there is that how do we reason about this invariance in different information regimes? And understanding that is a key step in developing maybe better tools. So what is the safety control problem? This is a very classical control problem where you have some possibly nonlinear system, you have some control authority U, you have some disturbances, and you want to find a policy, and you also have your spec that's some safe set X safe. And you want to find a policy together with a domain where this policy is valid. This policy maps your history of states and inputs to a new control input in a way that whenever you start within this good set W, you are guaranteed to stay in X safe indefinitely if you are using this policy. And this is a very standard problem. It's in a sense a two-player game between the control and disturbance inputs. And I think most of the previous speakers already mentioned types of this problem. So depending on which community you go, people might be talking about controlled invariant sets. People might be talking about viability. People might be talking about Hamilton-Jacobi-Isaacs type equations, but they are all essentially solving this problem. And it goes back to some earlier results from Bert Sekas, and there's a dynamic programming way of solving this problem that gives you the best possible control policy and best possible set, which is the maximal controlled invariance set. And the continuous time version of that dynamic programming problem is your Hamilton-Jacobi-Isaacs problem. And if you find any inductive invariant inside your X safe, by inductive invariant, what I mean is that if you start within a set, if you can remain in that set in one step, that's called an inductive invariant. That gives you a valid W, and that gives you a valid policy as well induced by this controller. And there is also, it's known that there's a memoryless maximally permissive controller that's induced from this maximal possible W. So you don't need the history. You can just look at your current state and make optimal decisions. So what is missing in this setting? So there are a few things missing in this setting when you compare it to modern autonomous systems. The first thing is we are assuming we have access to the state. But in general, we have this weird sensors and perception modules. We usually don't have access to the state. We have some weird observation equation coming from vision. And these vision-based sensors are a little weird. If you look at this thing, you will see this flickering in the detection. Essentially, you might not even have an observation at each time, because you think if you are driving here using this perception module, you will see this car appears and disappears. And your controller will think, there's a car there, there's no car there. There's a car there, there's no car there. And it might not behave properly if you don't take into account such imperfections in your observation mode. But there's one other thing that's in autonomous systems. Typically, in the standard approach, we assume we can observe the state itself. But this is a lane keeping example where I can also predict the future of possible disturbances. So it's not only that I know the state, I might have information about this disturbances into the future. For example, in the case of lane keeping, typically the road curvature is taken as a disturbance in dynamics models. But you have your maps, you have your cameras, you know the future disturbances. So it doesn't, it's not a good strategy to use disturbance as an unknown. You might have these predictions, you might have extra information. And that information, if you can blend it into your safety controller, you can improve how safe you can be. So we have been thinking about these different information regimes, and we have a few results that we published. I will give you a list of these results. Then I will switch back and talk about the initial problem that I tried to motivate. So we have thought about how to incorporate these predictions of disturbances, and we have some results in that domain. The interesting thing there maybe is that once you have these predictions, you can embed that to your dynamics and write down a very high dimensional system model, and you can try to solve a standard safety problem for that high dimensional system model. But you don't want to work with high dimensional system models because these approaches usually don't scale well. And we have shown under certain circumstances, you can solve the safety problem in a lower dimensional space and get an equivalent maximal invariance set where you do a lifting at the very end with very simple algebraic closed form operation. So you do your iterative approach in a low dimensional space and you can lift that set. So we have some results on how to do this in partial information without noise. We have some results on how to do it with imperfect information in a special case where you have noisy measurements, but your observation map is nominally invertible. And we have some results on how to do this when you have missing measurements, and maybe some idea of this missing measurement pattern. And theoretically, the type of questions we ask there is that in these different information regimes, is there a unique maximal winning set or operation domain? And if so, in what space you should define this maximality? Because sometimes it's not the state space, it's some lifted space with predictions or with beliefs. And what is the right space to think about maximality? Is there a best controller? That's another question. I said for the classical setting, we know this memoryless controllers are the best. But in these different information settings, what is the structure of the best controller? And sometimes this best controller might be too complex. In this case, if we restrict the controller class, can we recover uniqueness of this best controller within that class and maximality of your invariant set induced by those type of controllers within that class? And can we improve computational complexity by restricting controller classes? So these are some of the problems that we are playing with in different information regimes, and I think these are interesting problems. And the solutions that we get from this more theoretical problems led us to think more carefully about this more practical falsification approach. Okay, so I won't tell you about all the things we did in that regime. I have the list of references. If you are curious, you can look at it. I will switch back and talk about falsification, how to use these ideas in the context of falsification. And as I said, the standard falsification setting, you have a black box system under test, and you are trying to find initial conditions and disturbances to drive this system into a place where it violates the specification. What we want to do is we want to bring in synthesis, and we want to use additional information you might have about your system. And the additional information we will use is, we will assume we have the model of the plant physics, but we don't know the controller itself. So we have a setting where controller is under test, but we know the plant model, and we will try to use this plant model to figure out this hard initial conditions and hard disturbance sequences to lead us to a violation. And we not only want to find a counterexample, we also want to be able to explain these counterexamples. So how do we do this? So this is just restating the problem setting. Let me add a few assumptions to what I already said. We will assume this plant model is simple enough. And as I said earlier, we have simple enough dynamics models. We will also assume the specification is simple enough. And for the purposes of this talk, it would be mostly invariance, meaning safety and reachability. And simple enough just means almost everything for which you can solve certain control synthesis problems. Okay, so any questions on what we are trying to do? Okay, I will continue that. So our approach is as follows. We will first ignore the controller altogether. So we don't know what the controller is, we will ignore it. And if you have a complicated spec, we will take the safety critical part of the spec. So if the spec is in some temporal logic, you can take a safety closure of that logic formula, and you will get a safety spec. Then we are in some sort of invariance or safety control problem setting. And we will consider two different problems. So the controller's problem here is invariance inside the safe set. So ideal controller will try to keep you inside the safe set. And the disturbance trajectory you are trying to find to violate the specification is solving essentially a dual problem. So it's trying to reach to this unsafe set. So if you think about disturbance having a policy, the good policy for the disturbance would be the one that's trying to steer you to the unsafe set. And it turns out that the domain of this disturbance policy and the domain of this controller are complements of each other. And if you can solve the synthesis problem, you get some information about the disturbances domain, and you can also get disturbance domain by solving a dual synthesis problem. Okay, so this is the problem we will solve from the perspective of the disturbance. Assuming controller is now acting against, controller is the best possible controller, we will try to see if disturbance has a strategy to get us to the unsafe side. And this is again something that I already said. For the controller, if it was a smart controller and safe enough controller, the validity domain of this controller would be the maximal invariance set. The best controller would have that validity domain. And this reachability problem for the disturbance, the validity domain of the policy of the disturbance that takes you to the unsafe set would be just the complement of this controller's validity domain. And as long as you can compute these things, you can get a part of this disturbance policy. And there are many methods for computing these things, as we discussed earlier. And even if you cannot exactly compute them, you can possibly approximately compute them. Okay, so for doing synthesis-guided falsification, our hypotheses are these 2 points. So we conjecture that hard initial conditions should be at the boundary of this controlled invariance set. Because if you're outside of the boundary, you know there is no controller that will achieve safety if the disturbance is smart enough. So if you start outside of this domain, you will get a trivial falsification. But if you are inside, you should go through the surface somehow. So some of the hard violations should go through this surface. And for the external inputs, your goal should be to reach to this validity domain of the best disturbance policy. So if you're already in the validity domain of the best disturbance policy, you already have a mechanism to generate these disturbance sequences. And if you are inside this controlled invariance set, you can use something like a model predictive control that tries to greedily steer you to the validity domain of disturbance policy. We implemented this idea based on this hypothesis, and we also plug in some of the software that I showed earlier from KAUST and Stanford's DARPA Grand Challenge code. And we could identify some bugs of these software packages. It turns out that in adaptive cruise control, they work quite well because they are very conservative. And for those of you who don't know, adaptive cruise control is the controller that tries to track a vehicle in front of you. And if there's no vehicle, it acts like a regular cruise control. And all of these controllers tend to break early, and they are quite safe. But one slight bug that we found is that they have, for example, in the KAUST code, you have this internal safe distance defined, which is this red line there. That's a safe distance they hard code inside their software. And sometimes their controller can violate that hard-coded safe distance. And for lane keeping, we can find more interesting violations. And since we are using this safety sets, we can also just put these sets on top of those controllers, and we can supervise these AI-based controllers just for the sake of safety. And those controllers will work as they like if it's not a critical scenario. And if they get into a critical scenario where safety is at risk, we can override their decisions using the sets that we compute and invariance-based ideas. Okay, so this can handle learning-based controllers, but so far I haven't seen anything related to perception. And I want to extend this a little bit and to show you how we can handle perception-based control. Okay, so I will change the setting a little bit. So I will have this partial information setting. Now I have some plant model. It's known as simple. It can be uncertain, but it's known as simple. And I will start with the sensor model. It's known and simple initially. And I will see how to use it for a complicated camera and perception module in the end. So our problem is very similar. Now we are trying to find both disturbances and measurement noise in a sense, so that together with an initial condition, we can steer the system to unsafety. So pictorially, I want to find one initial condition in a set of initial conditions that this vehicle or autonomous system can have. And from that, I want to be able to find this disturbance sequences that will steer me to the unsafe side. So if we step back and think about the verification problem, the way I would write my dynamic programming for this problem is through these set iterations. So you can imagine this is also related to the value iteration by using indicator functions for sets. So you start with the unsafe set and you try to find if there exists some disturbance sequences that will take you to this unsafe set in one step. But the problem here is that even if your dynamics is simple, these iterations require knowing your controller. And your controller can be complex, making it very hard to do the iterations. And in our case, the controller might not be even known to us. So how do we do these iterations when the controller is unknown and very complex? So one approach is you can replace this controller with the best possible control, and you can do these iterations, and you will get an inner approximation of this backward reachable set that you are trying to compute. But this set only tells you the set of initial conditions from which it's impossible to reach, it's impossible to avoid unsafety. Therefore, these are not necessarily interesting initial conditions, but we can try to extend this set further using queries of the controller. So we changed this standard dynamic programming or set-based iterations with 3 additional steps. We modified the first step and we add 2 additional steps. And the important thing here is that the second step and fourth step are independent of the controller. And the third step is a simple querying step. So you don't need to understand what's going on there, but the second step is just trying to find where it is challenging to satisfy the spec. Third step queries the controller in that challenging parts. And last step is this regular backward reachability step using that control, using the controller decision you query. And with that, we can compute this additional extension of this set, and we can still get an under approximation of the reachable set. And if that reachable set coincides with the initial condition, we will get our violation. Okay, so here is a simple example. Here's an autonomous boat trying to avoid an obstacle. There are 2 controllers. One controller is trying to go from the left, if it is on the left of the obstacle, and trying to go to the right if it's on the right side of the obstacle. The other controller prefers to go from the left whenever possible. And if it's not possible, it will go from the right. And our algorithm doesn't know which controller does what. But if we do this iterations, this is the purple set. And these are the blue sets that we extend via query. So there's an interesting insight here. Sensor noise is affecting your violations, or have the most impact on your violations whenever you have these decision boundaries of the controller. So this is maybe not that surprising from a control perspective, but algorithm has no notion of this continuity of a controller or a decision boundary, but it can figure out these decision boundaries automatically. And you can imagine in a complex neural network controller, you might not know where those decision boundaries are. Okay, we have some extensions in other application domains, from power electronics to other driving examples. And we can also extend this to settings where you have this complicated camera instead of a simple sensor model. And what we do in that case is that we are adding this fictitious noise term and combining the camera together with the controller and treating this entire pipeline as our unknown and complicated controller. And you can show that under certain conditions on the camera model, the violations that we find can be implemented on the actual system. And this is how we achieve the initial results that I showed you earlier in the talk. So we first tried it with some simulated environments and simulated vision systems and controllers there. Again, our algorithm can trick this controller to hit the obstacle. And this is the example that I already showed you. I think I am running out of time, so I will just, you already seen that we can trick the controllers to go and hit the car. So if you key takeaways, maybe focusing on system level specifications and system level analysis is important in these problems. So even if you verify individual components, it's not always clear how those verification results will lead to a violation or satisfaction at the system level. And here we are taking a system level approach. Understanding the safety control in different information regimes is something that helped us to come up with this practical algorithm, but I think it's in itself interesting, and there are lots of open theoretical problems there. And we propose this new falsification guided synthesis approach, and it has an interesting connection with machine learning adversarial examples in a sense. So if you think about machine learning adversarial examples, these examples occur in decision boundaries of classifiers. And similarly, the adversarial examples and violations that we find using our algorithm also occur in decision boundaries. And from controls, we know these decision boundaries has to occur in a controller if your state space has a hole. So there is some fundamental limitations on how robust we can be to sensing. Here are a few other things that we are playing with in our lab. We are also putting these things on real vehicles, and I will just stop there and I can take any questions now or later in the discussion part.
Oh, okay, thank you, Dr. Ozay, for your energy and giving this interesting and amazing talk.